Imagine a lone astronaut adrift in the vast expanse of space firing a gun. It's a scene straight out of a science fiction film full of flashing lights and booming sounds. But what would really happen? Would the bullet behave as it does on Earth? Would the sound be as deafening? The reality, as is often the case with space, is far more intriguing. Our fascination with this hypothetical scenario stems from a natural curiosity about the universe and the laws that govern it. We're accustomed to the rules of physics on Earth, but space, with its vacuum and zero gravity, presents a whole new set of conditions. Understanding the physics of firing a gun in space allows us to separate science fiction from science fact. It provides a glimpse into the fundamental principles that dictate motion, forces, and the behavior of objects in a vacuum. To grasp what happens when a gun is fired in space, we must first understand how it works on Earth. A conventional firearm uses gunpowder, a chemical that rapidly burns when ignited. This combustion produces a large volume of hot gas, which expands rapidly and creates immense pressure inside the gun's chamber. This pressure forces the bullet down the barrel at high speed. The expanding gas also produces the loud bang we associate with gunfire, a sound wave that travels through the air. However, space is a near-perfect vacuum, meaning it lacks the air that transmits sound waves. So, the dramatic sound effects of a gun firing in space that we see in movies? Completely inaccurate. In reality, it would be an eerily silent event. The absence of air in space has another intriguing implication: no air resistance. On Earth, air resistance slows down a bullet, limiting its range. In space, a fired bullet would encounter virtually no resistance. It would continue traveling at its initial velocity indefinitely, until it collided with another object or was influenced by a gravitational field. But what about the shooter? Newton's third law of motion states that for every action, there's an equal and opposite reaction. On Earth, the recoil from firing a gun is absorbed by the shooter's body and the ground. In space, the shooter would experience the full force of the recoil, propelling them backward with a momentum equal to that of the fired bullet. This highlights a crucial aspect of physics in space, the conservation of momentum. In a closed system, like the vast emptiness of space, the total momentum remains constant. Science fiction often takes liberties with physics for dramatic effect. Explosions in space, for instance, are typically depicted as massive fireballs, much like we'd see on Earth. However, without oxygen to fuel combustion, an explosion in space would be a brief, silent flash. Similarly, the trajectories of bullets in space are often exaggerated for cinematic flair. In reality, a bullet fired in space would follow a straight path, influenced only by gravity if it's near a large celestial body. While these Hollywood depictions might be entertaining, they underscore the importance of understanding real-world physics. Exploring these scenarios, even hypothetical ones, allows us to appreciate the complexities of the universe and the elegance of the laws that govern it.
If you like this video, please give it a like and share with your friends, and if you have any story of what-ifs, please share.